Okay, so a couple of weeks ago in the calculus class, uh, we discussed not we actually uh, the curriculum in my university taught the student about the intermediate value theorem, but I didn't teach the class myself. But it is interesting when I check the proof of the theorem on this book, the Real Analysis Introduction to Real Analysis by Bartel. The proof is somewhat involved, and I'm thinking that it seems I managed to have slightly simpler proof. So let's uh, write down first what is the statement of the intermediate value theorem. IVT says that let f be continuous on the closed interval AB if M is between FA and FB, then there exists C in AB such that FC is equal to M. Okay. So the idea is that, let's say this is A and that's B, and this is M. And we know that, let's say FA is below the line and FB is above the line. So somehow it will crosses the horizontal line, right? So then what I tried before, so let's construct a set S which is X in AB in, well, I can just use a closed interval such that A less than X, X greater than A, and Fx is bigger than M. Okay, so since f of b is above the line, then b is belong to S, right? So S is non-empty since b is element of S. S is non-empty since b is since b in S. Okay. Now S has a lower bound, which is A, right? So, and then clearly A is a lower bound of S. So non-empty set who has a lower bound, then S must have an infimum, right? So the infimum of S is, so remember that we collect elements in the interval AB such that its value is above the horizontal line. So then the intuition says that if we take the infimum, then we will take this guy. We will get that guy. And we will declare as our C. So let C be the infimum of S. Right? The existence of the infimum is guaranteed by the supremum axioms, supremum infimum axioms of real numbers, right? Every non-empty set has supremum if it has an upper bound, and it has infimum if it has a lower bound. So this set S is definitely has an infimum, and we call it C. And this C will be our candidate to be the input where the value is exactly equal to M. Right? So we claim that C is between A and B, and f of C is equal to M. This one is clear or not? This one is not clear. Maybe I should just take away this one. So can C equals to A? Okay, we will check later, right? So by continuity of F, so we want to show that f of C is bigger than M, right? Suppose f of C is less than M. Then by continuity of F, yes, opening. Sebentar, there exists, okay, I need to speed up. Yeah, there's delta positive such that fx is less than M for all x in the interval, right? But then by the definition of infimum, we can also find an element of this interval, especially greater than, okay, since C is equal infimum of S, there is y in the interval C to C plus delta such that, so since it is an infimum, if we take something something bigger than C, then we can find an element which is so this is the smallest at the biggest lower bound. So if we make it higher, then there should be something below it. Okay, so there is y in that such that y is in S, right? Okay, yeah. But y in S mean, but then Fy is bigger than m. This contradicts to the fact that for all x in that interval, its value should be less than m. Right? Contradiction. Okay. So then f of c cannot be smaller than m. Right? So f of c is greater than m. And we can use the same argument. Suppose f of c greater than m, and we can take by continuity of f, there is delta 1 positive such that f of c, f of x greater than m on the interval c minus delta 1, c plus delta 1. Okay? So, and we need to find another contradiction. So, contradicts to what? So if in that interval, so I think we can find something, a lower bound which is also bigger than c. So let's see the picture. So if it is here and then all of them greater mm-hmm. 10 is greater than m. Oh, then we can find. Oh, okay. Then this is not a lower bound, right? But then it is y in S. Y is smaller than C. Which y is this? Which is, but then for y in the interval c minus d1 comma c, we have y less than c, but fy greater than m. So y in S, but not bounded below by c. Contradiction. So since f of c is not greater than m and it is not smaller than m, therefore f of c must be equal to m. Okay. Well, is it simple? Well, the idea is simple. I don't know, the execution, it's you decide whether it is simple or not. Okay, it's Maghrib, time to stop.